This is not a particularly long lesson. The lead up to what's important takes a little bit of time, but once we get to what's important, it's a pretty basic idea. We're going to be finding the number of arrangements of items if items are repeated. What does it I mean by that? And we're going to also solve more permutation problems. Repetitions, this is what we usually call repetitions, are arranging items when some items are identical. So I have 3 Snickerdoodles, and I have 2 M&M's cookies, and I have 4 chocolate chip cookies. And because I have no shame, I'm going to eat all 9 of those cookies. Okay? I'm going to sit down, put on my favorite show, get my plate of cookies, glass of white milk, and I'm going to eat those cookies. The question is, in how many ways can I eat them, order-wise? And I want you to notice I've done a fairly nice job here. These cookies are absolutely identical. Those 3 Snickerdoodles, you can't tell them apart. But even if they are physically different cookies, they're the same kind of cookie. So when I say, how many different ways can I eat all 9 cookies, I've got S for Snickerdoodle, M for M&M's, and C for chocolate chip. This is an arrangement of them. I could be a very methodical person. I don't want to mix up my cookie palette in eating these, so I eat the Snickerdoodles first, then I eat the M&M's, then I have the chocolate chip. Or I could do something like that. I could go, I'm after variety. And because there's 4 chocolate chip cookies, I end up eating 2 together just out of chance. But each of these arrangements is an instruction for how I'm going to eat the cookies. So what we're really talking about when I say how many ways can I eat these cookies, I'm saying how many ways can I arrange these letters? Because each arrangement is a way to eat the cookies. If I had these vehicles, toy cars, real cars, whatever, I have a blue, 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 red, 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 and I have 4 purple, purple cars. How many ways could I park them in a line? Well, ultimately what I'm asking you is, how many ways can I arrange those letters? Because each of those arrangements is a way to park them in a line. But I want you to notice that if I were to take this blue car and this blue car, blue, blue, red, 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 pink, 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 purple, whatever. If I were to take this arrangement, they're all parked out in a lot somewhere in a line, and I did this. I took the keys to this vehicle and I moved this vehicle here and I moved that vehicle there. It's the same arrangement. So even though the cookies were actually different cookies, or even though the cars are actually different cars, the arrangement of the cars or the order that I eat the cookies, if I eat these 2 Snickerdoodles in one order or the other order, it's the same big picture. So we're going to do a little review first just to warm up our brains. And this is good because most of the questions that were asked about when we went over Friday's stuff had nothing to do with permutations, most of them. In how many ways can all of the letters of the word oranges be arranged if there are no restrictions? This is like stealing candy from a tired baby. Unless I'm mistaken, there are 7 letters in oranges. Is that right? Did I count correctly? The answer is 7 factorial. Or, I don't know, this is overkill. I don't think you need to go 7p7, but it is 7p7. Or, I hope that none of us need to resort to the fundamental counting principle for something like this. 7 times 6 times 5 times 4 times 3 times 2 times 1. Bottom line, is it 5040? Is that number? It is. Bottom line is it's 5040. In how many ways are there to arrange all of the letters if the first letter must be an N? Well, there are a number of ways to approach this. This must be an N, and this is a free-for-all. This is open. I mean, you're arranging the letters, so you can't use the same letter twice. So the fundamental counting principle says that this is 1, and this is 6 factorial. The answer is 6 factorial. I don't know, maybe I'm in the minority here, but when I look at this question, if the first letter must be an N, what I do is I say the following. If the first letter must be an N, then let's not worry about the N. Let's just arrange the other 6 letters, which is where the 6 factorial comes from. How many arrangements of all of the letters of the word brains are possible? If the letters B, R, N, and S must be together? Well, this is at the heart of this problem. It's a Joan and Emily standing together problem. Except it's not Joan and Emily. It's Brianne, Rebecca, Nadine, and Sandy. Those 4 individuals have to be grouped together, and the A and the I don't have to be, but they might be just by chance. So what ends up happening here is you have the B, R, N, and S together. The A and the I may end up being together or not, but at the heart of the matter, we're arranging 3 things. We're arranging the A, the I, and all of the consonants. Turns out they're consonants. So the number of ways to do this is 3 factorial. What else do I need to include in my calculation? Because we have to arrange those 3 things, and we have to do something else.
4 factorial.
Right, we have to also arrange those 4 items, so we get 4 factorial. Is that 144? Starting to see a couple of nods. 144 ways. I'm all right. How many arrangements of all of the letters of the word pitcher if the vowels must be together? Well, this is Joan and Emily, but it's just leading up to something else. The I and the E must be together. We also have a P, a T, a C, an H, and an R. P-I-T-C-H-E-R. So I'm arranging, when I count these, I'm arranging 1, 2, 3, 4, 5, 6 items. It's 6 factorial. But I also have to arrange the vowels, the I and the E, which is 2 factorial. And that gives me, I think, 240. I'm pretty sure, but I don't want to move on unless you're sure as well. No. My mistake. 1440? Thank you. I made the mistake of thinking 6 factorial was 120, but that's 5 factorial. 6 factorial, 720 times 2 is 1440. Now, the reason why I'm giving you this question here, even though it's the Joan and Emily question, which we just did, even though it wasn't Joan and Emily, is because you need to answer that question to answer this question. And in the future, you're expected to be able to answer B without me prodding you and giving you help by saying, do A first. The only way you can ever find out how many ways these arrangements can be completed if the I and the E are not together is to find out how many ways they are together and take that away from the total number of arrangements. So the total number of arrangements here, 1, 2, 3, 4, 5, 6, 7, is 7 factorial, which gives me 5,040. This is the total. And as I said, you could do a thought experiment here to understand why this works. I give you 5,040 index cards, and on each index card, you write down one of those 5,040 arrangements. And then you stand, well, that's a lot of cards, but you have them on a table and you stand next to a big bin. And if the I and the E are together, you leave it on the table. And if the I and the E are not, actually, if the I and the E are together, you throw it out. And if the I and the E are not, you keep it. If you throw out all of the I's and E's together, you're subtracting the 1440 from the 5040. So this is total, this is together. what you're going to get is not together. By my arithmetic, that's 3,600. Good. A little bit of review, just to keep us on our toes. All right. So, this warm-up is about arranging items that are identical, arranging those 9 cookies, arranging those 10 vehicles, or whatever number it was. We're going to start off by doing this question. How many unique arrangements of the 4 letters of the word past are there? Unique just means different. This is like saying how many arrangements are there? Well, it's 4 factorial, isn't it? I don't think you need to do this, but you could say blank, 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 blank. I have 4 choices for the first, then 3, then 2, then 1. And it's decreasing by 1 each time simply because I'm arranging them. I'm not allowed to use the P more than once. Anyway, that's 24. And sometimes I don't have much of a life, so I list them all here. You don't need to list them all, but I've listed them all. So no matter where you look in here, you will not find any of these that are the same arrangement. I know that might be obvious, but I think it's an important point. That this P-A-S-T, that's the arrangement P-A-S-T, and it only appears in one place there. And if I look at S-A-P-T, it only appears in one place. There's unique arrangements, there are 24. Now the question is, and you're not going to show any work for this, but we're going to reason it out. How many unique arrangements of the 4 letters of the word pass are there? Now I want you to notice that past is very close to the word pass. They're off by 1 letter. But the important thing here is there are 2 S's. So here is my list of all of the letters of the word past. And we are going to change this, everybody, to pass. This is going to become an S. All of these are going to become S's. And again, this is not how you would do this problem. Right? They're all going to become S's, and if you watch the screen, they're going to change. I've changed them all to S's. Like a cheesy magic trick. But now I want you to notice that over here we had the first word was past, the second word was pats. When those 2 T's change to S's, we get pass and pass. We get the same arrangement. And find another pair. Oh, spat. There's spat here, right? There's spat someplace else. We'll go here. Spas. Is spas someplace else? Right there, bottom left. So this was spat, and this was to pass. I don't know what that means. It doesn't mean anything. But as soon as we change those T's to S's, those 2 words become the same. And now what you discover is there are pairs. This is pass and this is pass. Asps, asps. Asp, asp. And no matter where you look, what we discover is there are pairs. None of these things appear 3 times, which means the answer to this question is 12. We've gone from 24 to 12. And finally, how many unique arrangements of the letters of the word SAS are there? Well, these are all of the arrangements of the letters of the word pass. We're going to go from pass to SAS, which means that this is going to become an S. All of these P's are going to become S's. I hope you see that what's about to happen is we're going to get a whole bunch of items that are identical. In fact, look at the first. These are all going to become S's. What will this become? This will become SAS. What will this become? SAS. What will this become down here? SAS. I mean, and you're not going to do it this way. I'm just showing you that we're going to get a whole bunch of duplicates. And if we were to count these all, we have SAS. I've already got SAS. Let's cross off all of the other SAS's. SAS, 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 SAS. We only have one SAS. We have SSAS. Gone. I've already included it. Included, 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 included. We have SA. Included, 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 and AS. We're down to 4. So the answer to this question is 4. What have we learned? We've learned that the word past has 24 permutations, the word pass has 12 permutations, the word SAS has only 4. What do you do, see if you can figure this out, and I don't know if anybody will, but what do you do to the 24 to get to 12 that's connected to the word pass? Okay?
Divide by the number of letters that are the same.
Divide by the number of letters that are the same. Perfect. If I take 24 divided by 2, I get 12. Will that work in going from 24 to 4? Because I have 3 letters that are the same. If I take 24 and divide by 3, I don't get 4. So your rule that you came up with works for going from pass to pass, but we need a more general rule. And Miles, I think you have it.
Yeah. So you just divide 12 by 3. The next.
True, but I'm interested in, you're right, I'm interested in what do you do to the 24, because this is going to be the rule. What do you do to the 24 to get the 4? And it's got to be connected to the word SAS.
Divide by 3 factorial.
You divide by the factorial. So, I mean, 2 factorial is 2. But if we take 24 divided by 2 factorial, you get 12. And if you take 24 divided by 3 factorial, you get 4. 3 factorial, 6. So this is the rule. The rule is, if you're arranging a number of items and some appear more than once, then you have to divide by the factorials of the numbers of times multiple items are repeated. In other words, if you're arranging n items and one item occurs A times and another one occurs B times and another one occurs C times, this is what you need to do. If I go back to my cookie example, I'm arranging 9 items, which would mean it would normally be 9 factorial, but I have 3 snickerdoodles, and I have 2 M&Ms, and I have 4 chocolate chip cookies. Just to make sure we know how to use our calculators, let's all calculate that, please. I mean, if I were doing this, I know what 3 factorial is, I know what 2 factorial is, I know what 4 factorial is, but I'm going to use the factorial function. I would do it this way. This is how I would enter it. This is just the way I was taught math. Since you're dividing by those 3 things, you have to divide by each of them. Or what you could do instead is you could go 9 factorial, divided by, and then put brackets, and then just go 3 factorial, 2 factorial, 4 factorial. I mean, as I said, I know what 3 factorial is, it's 6. I find if I have to go into my menu to find out what 3 factorial is, maybe I should learn something from that and just go, oh, it's 6. 2 factorial is 2, 4 factorial is 24. Anyway, the answer is 1260. If I said how many ways are there to arrange these 10 vehicles, you would take 10 factorial, you'd divide it by 4 factorial, you'd divide it by another 4 factorial, you'd divide it by 3 factorial. And I misspoke. You would take 11 factorial because there are not 10 vehicles, there are 11. So this would be 11 factorial over 4 factorial, 4 factorial, 3 factorial. 4 factorial times 4 factorial is 4 factorial quantity squared. Don't try to wrap your head around what the number should be. I mean, it might be deceiving. It might be deceivingly large or deceivingly big, depending on the situation. All right, we're just going to do a couple of examples now. How many arrangements of the letters of the word calculus are there? And I'm going to show you, this is really a simple question, except that it is so easy to make a mistake. It really is. So my recommendation is to start off by saying I have 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 factorial. And now I need to divide by the repetitions, factorials. I find that if students just look at the word and write down the repetitions, sooner or later you make a mistake. So I would recommend starting on the left and saying I'm going to look at the C. Oh, there's 2 C's, and I cross them off the list. So now I have a 2 factorial on the bottom. And then I would go to the A, I would cross it off, and I would move left to right and see there are no more A's, so I'm done. I would go to the L, and I see there's 1, 2 L's. I cross them off, so I make sure that I don't count them twice. So that's another 2 factorial. I go to the U's, I cross them off, that's another 2 factorial. And there's 1 S, it's not repeated. This is the answer to the question. I am curious how many of you see that the answer to the question is 7 factorial. Because the bottom of this expression is 2 factorial, 2 factorial, 2 factorial. That's 2 times 2 times 2, which is 8. 8 factorial over 8 leaves 7 factorial. I'm pointing this out to you because if you see this question on a multiple choice, and this is one of your choices, people look at it and go, wow, there's no way it's 7 factorial. There's repetitions. I know there's 8 items. Where are they getting 7 from? But it would be the right answer. That is the only question we're going to do about arranging these items like cookies or cars. The rule is pretty simple. Let's take a look at a totally different question. I actually remember being in junior high. I might have been it was grade 8 because it was Mrs. Kenny. And I was sometimes maybe not, I was a bit of a problem in the math classroom because I could get my work done and I would just bother people. Or me and my buddy Steve would bother people because we would just get the work done. And so this would be something that Mrs. Kenny would give Steve and I to keep us busy. And it did. And it also taught us a lot about numbers. She was an incredible teacher. How many ways can Jillian go from home to school if she always has to get closer? In other words, Jillian is not allowed to do this. Jillian is not allowed to dawdle. If she were allowed to dawdle, the answer would be infinity, right? She always must get closer. So Mrs. Kenny explained to Steve and I that basically, she didn't maybe explain it this way, but I'm going to, you can move in this direction or you can move in this direction. You always must get closer to the school. And the question is, how many different ways are there? And this is a difficult question. If you tried to trace them out, you'd lose your mind a little bit, I think. And I think we probably did. We would probably just give up. Especially when you start looking at things like this, which is more complicated. So the idea here to solve this at a Math 30 level is that we must move, I'm going to use L for left and U for up. Okay? We could use north instead of up, and we could use W for west instead of left. And I'm going to draw in one path, one particular path. This path is maybe not a very interesting path, but that's, bless you, one of the things you could do to get home, one of the things Jillian could do to get home. And I want you to notice that that path can be written out as L, U, 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 L, 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 U, L. Left, up, 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 left, 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 up, left. So if Jillian wanted to take a different path home every day, this would be one of the sets of instructions on telling her how to get home. But if I were to take a look at, and I'll get to the point, and it's not a difficult one, but I think I want to really make sure you understand it. If Jillian were to instead do that, then what would that be? Well, that would be, I missed a little piece there. That would be left, left, up, left, 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 up, up, up. Are we in agreement on that? Yeah? What am I getting at? I'm getting at this. Each arrangement of those letters is one way to get home from school. So what the question really is how many ways can we arrange left, 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 up, 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 up. Did I get the counting right? Is there 5 lefts and 4 ups? So this is the problem. How many ways can you arrange those letters? Because each of the arrangements is a path home. Well, the answer is really simple. It's 9 factorial over 5 factorial, 4 factorial. Because we have 5 letters that are the same and 4 letters that are the same. I don't know if there's anybody in here who has taken Math 30-2 prior to being in this class, but in Math 30-2, Miss Allen would show you a different way to do this problem. Okay? And in this level, I wouldn't recommend it. And I don't know if that applies to anybody or not, but I just wanted to say it. What the answer is, I guess it's not irrelevant. We do want to know, but finding it is not a big deal. 9 factorial, I want to divide by 5 factorial, and I want to divide by 4 factorial. I happen to know what 5 factorial and 4 factorial are. You can use your factorial function key to get there. 126. So imagine little Steve Bedinsky and me in grade 7 or 8 trying to trace 126 different paths. It would just be a nightmare. It would be a spider web of stuff. 126. Final question. How do I get from A to B always getting closer? Well, I can only move this way or this way. I can only move right or down. But I can't do this in one shot. What I have to say is I have to go from A to C and from C to B. This is the only way to solve this problem. So I need to go from A to C and C to B. And means times. So how many ways from A to C? Well, look at the diagram. I need to make from A to C left. Nope. I need to make moves right, 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 down, 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 down. I need to make 4 moves to the right, 3 moves down. So I need to make a total of 7 moves, but I need to divide by 4 factorial, 3 factorial. I want to say that's 35. There are 35 ways to reach C from A. How many ways are there to go from C to B? Well, C to B involves right, right, down, down, which would mean we're arranging 4 items over 2 factorial, 2 factorial. That's an easy one. That gives me 6. It's Bobby Bear. It said Bobby Bear no longer has 3 pairs of pants and 2 shirts. Bobby Bear has a whopping 35 pairs of pants and 6 shirts. I don't know why the imbalance. Okay. How many ways can he get dressed? 35 times 6. That's where that and comes in. So we have 35 times 6, which is 3 times 9. That's 270? No, 180. I'll get it. 210. Thank you. So there are 210 different paths to get from A to B. And that's the only way to do it. Again, if you've seen this in other classes, Miss Allen has a different way of doing it, because in Math 30-2 it needs to be done that other way. Interestingly enough, if you use Miss Allen's approach, you can solve more complicated problems that this one can't solve.